Hello and welcome. As we continue our discussions, we are looking in this particular instructional video and this particular inquiry activity at what is called Coulombic Attraction. So basically this is setting us up for a future topic, which is going to be ionic bonds and forming ionic compounds. And we're going to talk a little bit about what is Coulombic attraction and how does that come into play when discussing chemistry, and in particular when we talk about bonds that are going to hold those compounds together. So what variables will affect the force of attraction between charged particles? And we talked about charged particles before, if you remember, when we mentioned ions. So we talked about how ions basically are a neutral atom of a particular element that has either gained or lost electrons, therefore giving it either a positive or negative charge, and they are called ions. So Coulombic attraction is the attraction between oppositely charged particles, positive and negative. For example, the protons, and those are in the subatomic region, in the subatomic level, the nucleus of the particular atom. So the protons in the nucleus of an atom have attraction for the electrons which are around the nucleus. We're going to talk later on about the electron cloud and where those electrons reside. This is because the protons are positive and the electrons are negative. This attraction force, it can be weak or strong. And in this activity, we're going to be looking at how we maybe look at the strength, or we measure even the strength of attraction between protons and electrons in these different atomic structures. Here's Model 1. It says distance and attractive force. So all we're doing in Model 1 is showing that there is a relationship between the distance that two particles are apart from each other and the attractive force, in particular the magnitude of that force between those two particular charged particles. Question number 1 says, what subatomic particles do these symbols represent in Model 1? Well, plus would be a proton, negative over here would be our electrons. So we've got our protons and electrons, positive protons, negatively charged electrons. Would you expect to observe attraction or repulsion between the subatomic particles? Opposites attract. Okay? So opposite charges attract, so we're expecting to see attraction in this case. What are the independent and dependent variables in the data? Well, we're looking at a relationship between distance and attractive force. So if you have the ability to actually move protons and electrons around, it is the distance that you are changing. You're choosing at what distance do you place the proton and the electron. So the distance here, these three distances, that is the independent, and the resulting force, the magnitude of the force, is going to be your dependent. Alright, and if you'll notice now the relationship, we can determine, not with any quantitative calculation or amount. We're basically just going to make an observation of the relationship. A complete sentence that describes the observed relationship between the independent and dependent variables in Model 1. So if you notice, as the distance increases here, the magnitude is going from 2.3 to 0.58 to 0.26. All of these are the same powers of 10 multiplied by the same power of 10. So the distance is decreasing the force is decreasing as the distance increases. As distance goes up, as it increases, the force is going to decrease. That is an inverse relationship. If the distance between a proton and electron is 0.5, would you expect the force of attraction to be greater than or less than 0.26 times 10 to the negative 8? Well, let's find 0.5. up here, and it's not up there. It's actually much greater, not much, but greater than any of the values that we have. So we would expect it to be less than the 0.26 that is given there for the 0.3 nanometers. NM, by the way, is nanometers, very tiny measurement. Okay? So we'll expect that to be less than. And if two protons are 0.10 nanometers away from one electron, would you expect the force of attraction to be greater than or less than 2.30 times 10 to the negative 8? Well, in this case, two protons, if I've got another proton here at the same distance, we're comparing it to this force of the attraction when there's only one proton. We would expect it to be greater. If one proton is going to pull on this electron right here with this magnitude, this force, 2.3 times 10 to the negative 8, if you had two protons, you would expect it to be a greater pull on this electron, greater than the existing force there when there's just one. Okay? Model 2, the alkali metals. By the way, these alkali metals are in group 1 on the periodic table. If you look at the periodic table, excluding hydrogen, hydrogen also is in group 1, but we'll just ignore that for a little while. These are the alkali metals, and we're going to notice there's something similar about all of these, and we're going to talk about also what's different, because they're going to have a pull on their electrons. The pull is from the protons that are in the nucleus here. So you've got protons in the nucleus, and you've got electrons around it. Okay? And these arrows are indicating that the stronger the force, the thicker, bigger the arrowhead. Okay, or the arrow altogether. The arrows represent the force strength. Okay? And in number 6 here, B, the thicker, I just said this, didn't I? The thicker the arrow means the stronger the force. Number 7, using a periodic table, locate the elements whose atoms are diagrammed in Model 2. Are the elements in the same column or the same row? Those are all in the same column. They're all, as I mentioned, in group 1. Okay, number 8, circle the outermost electron in each of the diagrams in Model 2. Circle the outermost electron. Well, let's just go up here. Let's find the outermost. There's the outermost electron, outermost electron, outermost electron. These electrons here are diagrammed in kind of like orbits around the nucleus. That's not exactly how the electrons are located around the nucleus, but it's just a model. We're just showing that lithium has 3 electrons. Here are 2. And then at a higher energy level, further from the nucleus, there is a 3rd. And same thing here, sodium has 2 at the lowest energy position, the closest, if you will, the closest circle or the closest region around the nucleus. And then it's got 2, 4, 6, 8 more at the next level, and then a single one at the furthest distance as well. Potassium has 1 single electron at the furthest distance from that nucleus right there. As you move from the smallest atom to the largest atom in Model 2, how does the distance between the outermost electron and the nucleus change? It increases. So as you add more and more electrons, that means there's limited space. The outermost electrons are going to be further and further from the nucleus. As you move from the smallest atom to the largest, how does the attractive force between the outer electron and the nucleus change? It goes down. Further and further away. Are your answers in part A and B consistent with the information in Model 1? Yes. because we already determined that as the distance increases, the force is going to decrease. Model number 3, this time notice what is constant. We are not changing the distance. All of these are at a distance of 0.10 nanometers. What is changing is the number of protons. And so now we're going to see, what if we increase the number of particles? How does that affect the force of the attraction? And you can already see what's happening here. In this case, the independent variable is number of protons. Dependent variable, again, is just going to be the force. Write a complete sentence. In this case, as the number of protons increases, then the force of attraction, or in particular the magnitude of force of attraction, is going to decrease. Sorry. It's going to increase as well. My apologies. Alright, number 10. What would be the attractive force on a single electron if 5 protons were in the nucleus of an atom? Show mathematical work to support your answer. Okay, so basically what they're saying here is, if you've got 5, let's go back up here. We've got 1, 2, 3, and 4. Now they're saying, what if you had 5? Well, you may notice here that this initial value, where there's only 1 proton acting on 1 electron, is then doubled. It is then tripled. It is quadrupled. Every time you add another proton there, the number of protons is going to impact this force, and you're going to basically have multiplied by a certain factor, multiplied by the number of protons you have. So if we have 5, we would have to take this initial value here and multiply by 5 in order to get the force of 5 protons acting on that electron at that distance. Just 5 times the 2.3 times 10 to the negative 8. And this is in newtons. So you can do that on your calculator. Number 11, imagine that a second electron were placed to the left of a nucleus containing 2 protons, model 3, set D. Predict the force of attraction on both the original electron and the second electron. So let me repeat this. You have a second electron, and it's placed to the left of the nucleus containing the 2 protons. So what's going to happen here, in this case, you have, let me just kind of draw it here for you. If you've got 2 protons and an electron here on the right, imagine on the left side, the same distance away, you've got another electron. Same distance away, but at the opposite side. Okay? The question is, what is going to happen? Well, if you had the opportunity to discuss this with somebody, you might figure out that some people are going to have different opinions here, okay, which is okay. But some of you may say that the attractive force would be this same value. It's just the opposite direction. The 4.60 times 10 to the negative 8. It's just that these protons have an attractive pull on this electron, but it is just going to be on the opposite side. It's just the direction that it changes, but the magnitude is the same. Okay? But the opposite side. Okay, some of you may have said that you're going to have that the force is going to basically be kind of halved, because you're thinking that the force now is split between the electron on the right and the electron on the right. Okay? Well, I'm not going to give this away quite yet. Let's move forward and see which of these hypotheses is actually correct. Alright. The attractive and repulsive forces in an atom are rather complex. An electron is attracted to the protons in the nucleus, but it is also repelled by the other electrons in the atom. Keep that in mind. It is important to note, however, that the attractive force of the nucleus is not divided up among the electrons in the atom. That is very, very important to know. So as you add more and more electrons, you don't take that attractive force and begin to divide it by however many electrons you have. Each electron, this is a key point right here, each electron gets approximately the full attractive force of the nucleus. Now, as I said before, there are some repulsive effects of other electrons. Some of those electrons are going to push away from each other, and so that may affect the overall magnitude of the force that the electron is feeling from the nucleus. But the key point here is that each electron will basically get the full attractive force from the protons in the nucleus. Okay? And let's look at this model to kind of help us figure that out. So looking back at the question there that maybe you had some different opinions on, it would be the same magnitude but just the opposite side. The electron on the right side over here is going to feel the same attractive force as the electron on the right side. Left side and the right side. Okay? So here we have two protons, and we have an electron on the right, an electron on the left. They're equal distances apart, and both electrons are feeling an approximate pull of 4.60 times 10 to the 8. That would be newtons, by the way. Excuse me. What is the approximate attractive force on each electron below? Well, in this case, each electron below, you have 3 protons pulling on electrons, and all of these are the same distance away. So in this case, they're all going to feel the same. We got to look back up here to find it. Here we go. 3 protons are exerting a force of 6.90 times 10 to the negative 8 newtons on a single electron. So every one of those is going to feel the same force. I'm assuming that this is also 0.1 nanometers. So they're all going to feel a force of 6.90 times 10 to the negative 8 newtons. Okay? Alright. These elements are in period 3. So if you look on the periodic table, that would be the third row. The third row on the periodic table, if you go down to the third row, you're going to see sodium going across, keep going across, aluminum, and chlorine. They're not right next to each other, but they're all in the third row. Okay? Now this time, let's just make a little observation. You'll notice that all of the outermost electrons are pretty much the same distance away from the nucleus for these atoms. What is different though is you still are going to have a different force. So notice this is very strong force. This one is weaker, or the weakest of these 3. What is it now? It's not the distance. The distances are all pretty much the same. It's not the distance in this case. It's something else that is determining the pull on the outermost electron. Locate the elements whose atoms are diagrammed in Model 4. Are elements in the same column or same row? I just said they're all in row 3, right? Circle the outermost electrons in each of the atoms. We did that already up here. Which of these atoms diagrammed in Model 4 has the strongest attraction? Here's your strongest one right there. And consider the information now in Model 4. It says, as you move from the smallest atom to the largest atom, Does the distance between the outer electron and the nucleus change significantly? No. Even though it may be slightly bigger, this one's got more electrons, okay, chlorine has more electrons, but the size of these are not hugely different. So the distance here between the outermost electron and the nucleus is pretty consistent for all of these. Can the differences in the attractive force shown by the arrows be explained by a change in the distance of the differences in the attractive force be explained by the distance between the electrons? So here's what they're saying. There is a difference in the attractive force, but is it because of the distance? No, because the distance is not a huge change. So it's something else that is causing the force of the attraction here to go from weak to a little stronger and then strongest. Let's write the number of protons located in the nucleus of each of these atoms. So if we do that, the sodium has 11 protons, so there's 11 protons in here. This has 13, aluminum is 13, and this one has 17 protons. So now you can begin to see, oh, it's not the distance that's making the Coulombic attraction stronger as you go from sodium to chlorine. It is the number of protons. All of these protons, 17 protons pulling on that same outermost electron that's about the same distance as the aluminum's outermost electron, but aluminum only has 13 protons and sodium only has 11. That's what's explaining the reason behind the stronger pull on the outermost electron. It is the increase in protons in the nucleus. Yes, as the number of protons increases, then the strength of the force is going to increase as well. For each set of elements below, circle the element whose atoms will have a stronger attractive force between their outermost electrons and the nucleus. Basically, we're looking to see which of these atoms has the greater number of protons, which will have the stronger attractive force between their outermost electrons and the nucleus. If we look at Ba and Ca, what you want to do here is you want to consider, are they in the same column or are they in the same row? If they're in the same column, then it's going to be the distance that is going to determine the strength of the Coulombic attraction. The larger atom, as you move down the group, the larger atom is going to have the weaker attraction because the outermost electron and the nucleus are farther apart. As you move across the row, the size of the atoms are not changing that dramatically, and so it's going to be the number of protons that is going to have the greater impact on the force. And that means as you move further to the right, the number of protons increases, so the force is going to be greater. Okay? So, barium and calcium, find them on the periodic table. Are they set up in the same group? If so, the one that is higher on that group is going to be smaller and is going to have the greater Coulombic attraction, the greater force. Or are they in the same row? If they're in the same row, then the one that's further to the right is going to have more protons in its nucleus and is going to have the greater force. So go ahead and check that if you haven't already, and then I'll share the answers with you here. So between barium and calcium, it is calcium that has the stronger force. Between chromium and copper, it is copper. And between argon and xenon, it is argon. Okay? Alright, last part here, the extension questions. Consider the atoms diagram in Model 2. We'll go back up to Model 2 in just a second. On each diagram, write the number of protons in the nucleus of the atom. So if we were to do that, Model 2, lithium has 3, sodium has 11, and potassium has 19. Okay? So 3, 11, and 19. When comparing elements in the same column of the periodic table, which factor, distance to the nucleus or number of protons in the nucleus, seems to be the dominant factor for determining the attractive force between the outermost electrons and the nucleus? So we already talked about this. In the same column, it is going to be distance that is going to be the main contributing factor for determining which atom has a stronger Coulombic attraction, stronger force. So remember, as distance increases, the force is going to decrease. And distance increases as you move down the column. For a particular row, it is more dominant in this case, it is going to be the number of protons. As they increase, the force is going to increase as well. And as you move from left to right, the number of protons increases. So the ones on the further right part of a particular row are going to have the strongest force between the outer electrons and the nucleus. Describe the mathematical relationship between the distance and the attractive force between protons and electrons. So basically, the force and the distance are inversely related. Okay? Inversely related to distance. More specifically, it is inversely related to distance squared. So you would have a relationship like this, which basically says force is proportional to, that's what that symbol means, proportional to the inverse of distance squared. The mathematical relationship between the number of protons and the attractive force between the nucleus and electrons. In this case, F, the force, is directly related to the number of protons. So F, force, is proportional to the number of protons. Directly proportional. Up here, it's inverse relationship. Here, it's a direct relationship. Okay? All right. I hope that was helpful, learning a little bit about Coulombic attraction and learning that the distance between particles is going to have an influence on the force that they feel, as well as the number of particles is going to have an influence on the force that they feel, that Coulombic force between positive and negative particles. All right, great job, and we will see you in the next video.